Any rock can be metamorphosed, that is, have part or all of its mineral content and structure changed atom by atom while a rock is still in a solid state. So metamorphic rocks differ from igneous rocks, all of which originate from a melt, a magma. Metamorphism is caused by significant change in the environment that created the rock. Heat alone can cause metamorphism. Under the continents, the geothermal gradient increases an average of 20 degrees Celsius per kilometer of depth, attaining 100 degrees, the boiling point of water, only 4 kilometers down, and ranges up to almost 300 degrees at 10 kilometers, 6 miles. That is enough heat to cause replacement of one mineral by another. As pressure too rises with the increasing weight of overburden, at greater depth, the structure of the rock is altered more decisively, and its mineral content mutated to a greater extent. When water or mineral-bearing fluids are involved, transportation is effective over a wider range of environments. This chart shows a very elementary classification of metamorphic rocks based on the temperature at which they form and their structure. Either foliated because of the effects of pressure on certain minerals, or non-foliated. Foliated rocks are divided into 3 classes according to a range of temperatures and degrees of stress that are reflected in the intensity of alteration as indicated by crystal size and the kind and grade of foliation. Slate is derived from a shale or claystone by stress from one direction that causes chlorite and many clay minerals called sheet silicates to grow at right angles to the stress. The grains are still not visible to the naked eye, but produce a slaty cleavage that causes the rock to split into thin, parallel laminae. Schist may form from any rock subject to considerable stress and heat ranging from 300 to 450 degrees Celsius. Visible sheet-like crystals, mainly biotite and muscovite, aid in the development of a nearer planar foliation, but quartz and feldspar, along with a number of other minerals, are not oriented or deformed. Gneiss represents even stronger stress and higher temperatures. The sheet silicates become unstable, and dark-colored minerals like hornblende and pyroxene appear and become segregated in parallel bands. These minerals, although their crystals are elongate, not sheet-like, still have a preferred orientation with the long axis perpendicular to the maximum stress. Granulites and eclogites are not listed on the chart. Both indicate metamorphism by heat at more than 500 degrees Celsius. In addition, eclogite forms under very high pressures. All of the hydrous minerals and sheet silicates are unstable under these conditions. In granulites, few of the minerals still present have a preferred orientation, and their grains are rounded and set close together, so its texture is called granulitic. But eclogites are coarse textured, for they cool very slowly. Migmatites are metamorphosed rocks in which heat or friction has caused susceptible minerals to start melting. The darker areas on this slide are sites where melting has begun. Metamorphosed unfoliated rocks are restricted to limestones converted to marble and quartz sandstones in which the quartz crystals have grown to interlock and fill any former intergranular space. Neither includes minerals with sheet-like or planar orientation, so the metamorphosed states are not foliated, although metamorphosed argillaceous limestones and sandstones present a banded appearance. As stated, the chart is very elementary. It broaches neither the 6 types of metamorphism nor the 9 commonly recognized facies, nor does it have data regarding the role of depth of burial. This one does. It shows the ranges of both temperature and pressure in relation to depth of burial, and defines the limits of the several ranges of heat and pressure that control the intensity of metamorphism. The geostatic pressure of 1,000 megapascals, 145,000 pounds per square inch, at a depth of 32 kilometers is already very great, but it is far less than the pressures encountered at greater depths. The relationships of the 3 commonly used measures of pressure, pounds per square inch, bars, and pascals, are shown on this slide. Pascal is now the internationally accepted measure, although bars are still used by many atmospheric scientists. 14.5 pounds per square inch equal 1 bar. 10 bars equal 1 megapascal. The curve of this generalized geothermal gradient shows that heat begins to liquefy some low melting temperature felsic minerals at 600 to 900 degrees Celsius at depths of 50 to 100 kilometers, while refractory mafic minerals melt only when temperatures are on the order of 12 to 1300 degrees Celsius at a depth of about 200 kilometers. These facts, in conjunction with the minerals present, make it possible to judge the type of metamorphism involved and the site at which it occurred. 6 types of metamorphism have been named: contact, burial, hydrothermal, dynamic, regional, and shock. Shock metamorphism takes place when a large meteoroid strikes the Earth. It does not fall within the scope of this elementary discussion. Contact metamorphism takes place when a body of magma is intruded into country rock. The range and extent of its effects depend on the location, size, temperature, and type of intrusive magma. Associated fluids, the metasomatic aureole of this sketch, can increase and expand the effects of contact metamorphism greatly. In general, contact metamorphism is most effective where the contrast in temperature between intrusive and host is greatest, that is, near the Earth's surface. Burial metamorphism occurs when rock units are buried several hundred meters to a depth where their temperature does not exceed 300 degrees Celsius. The new minerals formed under these conditions are of a low grade and differ but little from those related to diagenesis. Well, the 10-minute limit approaches, but we are not halfway through this slideshow about metamorphic rocks. Please go to part 2 for the remainder of this discussion. It begins with a summary of metamorphic suites and their facies. For example, what is a Barrovian suite, and what are blue schists and green schists?